Ladies and gentlemen, welcome to the 12th series of INA-IGS Geosynthetic webinar under the theme, Why is Geogrid so difficult to model in finite element analysis? This event is brought to you by the Indonesian chapter of the International Geosynthetic Society, or INA-IGS. My name is Rifa Nurkayungyun, and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this afternoon. First, I will be reading the rules of the webinar. Second, there will be an opening remarks by the President of INA-IGS, Bapak Budianto Wijaya. After that, the event will be guided by Bapak Michael Lobby as our moderator to start the presentation of our speaker, Andrew Lees. The event will then continue with a Q&A session. We would like to ask you to stay with us until the end of the event because we will be doing a quiz with a total of 250,000 rupiah for 2 winners. We will also give you access to the e-certificate at the end of this webinar. Ladies and gentlemen, for your own convenience, please put attention to the following rules. You can submit your questions for the speaker through the Q&A feature located at the bottom of the screen. The question should be in English. You can raise your question before, during, and after the presentation of the speaker. We expect you to stay with us until the end of the event to get the information you need regarding the e-certificates and also the soft copy of the presentation from the speaker. This event is also live streamed on INA-IGS YouTube channel, or you can directly go to the link bit.ly/INA-IGS12YT. If you have any questions, please contact Sandy at the number shown on your screen or on the chat box. Now, without further ado, I would like to invite the President of INA-IGS, Bapak Budianto Wijaya, to give his opening remarks. To Bapak Budi, the time is yours.
Good evening, ladies and gentlemen. As the President of INA-IGS, I warmly welcome and thank Dr. Andrew Lees as a speaker in our monthly webinar. Today is the 12th webinar organized by INA-IGS and the last webinar in the year of 2021. The target of this webinar, as we always strive to, is to share the knowledge and experience in geotechnical engineering, especially in geosynthetics. Hopefully, the seminar held will nurture deeper understanding of geosynthetics and becoming one of the go-to sources for geotechnical engineers. The kick-off seminar in 2022 will be held in February. I would like to express my sincere gratitude for the hard work of our webinar division led by Mr. Krisandi Saptianto and his team for a continuing success of INA-IGS seminars. Next year, INA-IGS will celebrate its 30 years birthday, and to celebrate the milestone, we are going to invite all of you to attend the conference in November 2022. We also note the rising need of industrial knowledge and applied engineering for university students and eager to be part of contributing partners. Kindly contact our secretary should your university are looking forward to have insightful and experienced engineer to share their expertise. It will be an honor to be partnered with universities all over Indonesia. I thank you for all our members and especially for all INA-IGS committees with help and bring INA-IGS to be a better, respected, and prominent organization. On behalf of INA-IGS, we welcome you all and wishing a Merry Christmas to those who celebrate and brighter and prosperous Happy New Year to us all. Thank you.
Thank you, Bapak Budi, for your kind remarks. To all audience, we invite you to join INA-IGS as individual members by registering yourself through the link bit.ly/member-INA-IGS. Ladies and gentlemen, now this webinar will be guided by our moderator, Bapak Michael Dobi. Before I give the floor to Bapak Michael Dobi, I would like to remind you that you can start submitting your questions from now, during, and after the presentation by using the Q&A feature. We would also like to remind you to stay with us until the end of the event to get the information you need regarding the e-certificates and also the soft copy of the presentation from the speakers. Now, please welcome our moderator, Bapak Michael Dobi. To Bapak Michael Dobi, the time is yours.
Thank you very much, Rifa, for your very, very clear and precise introduction. We've reached a special occasion today, as Pak Budi mentioned, the 12th of our webinars of this year, 2021. I think it's been an incredible series of events we've had. We've heard some incredibly interesting webinars and presentations, and I think you'll see today that we'll be carrying this through right through to the very end of this series of webinars. So I would especially, before I introduce our speaker, I would like also to thank all participants who take part and listen to these webinars. And I certainly hope that you've gained a lot of interesting facts and knowledge from these events. I believe we've covered a huge amount of topics and material in the last 12 months. And that will certainly continue tonight. I'd also like to echo Pak Budi's words of thanks to our organizing committee of INA-IGS, who look after these events. They send out the invitations, they arrange the Zoom practices and everything we do to try to make these run as smoothly as possible. The only problem we sometimes have is the internet. So I hope the internet is helping us tonight to give you a nice, clear presentation of this webinar. So I now would like to introduce our speaker tonight. As you've already heard, Dr. Andrew Lees. And in fact, Andrew is my colleague at Tensar, in fact, for the last 6 years or so. And in fact, Andrew is originally from the UK, he's British, but in fact, for the last 16 years, he's been living in Cyprus. I'm not quite sure how well in Cyprus is in Indonesia, but maybe it's something you could Google to find out exactly where it is. But anyhow, he's not that close to us, but he's a bit closer than somewhere like the UK when it comes to his time zone. He also set up a company called Geofem, which you'll see is mentioned there below his name, which is a company that specializes in using numerical techniques to assist in geotechnical and other civil engineering projects, as well as other techniques as well. I think there's a whole interesting webinar we could hear for other things that Geofem do, but tonight we'll just be hearing from Andrew. Also like to mention that Andrew is only our second non-academic speaker this year. All others have been academics, mainly professors or similar. However, what's very nice is that we have someone speaking tonight who is working in our industry. He does have earlier experience working in the academic field, but you'll see how he's, if you like, combined that sort of deep knowledge of a particular topic and is now applying it into practice, which I think is something really exciting. So Andrew has a deep knowledge and experience in finite element analysis, numerical modeling. And what I've seen over the last 6 years is how we have benefited from this knowledge. We have many colleagues now who've become much more competent at using these techniques. The techniques are used much more frequently to assist in projects and so forth. And he's also used these techniques to help actually develop design methods. And I'm suspecting you might hear something about that later on this evening. So it's been a great benefit, and I think Tensar has gained greatly, including another special thing that Andrew does called Tensar Ground Coffee. I'm not sure if anyone has seen these, but I believe it's what's called a blog or something like that. Anyhow, but these are very nice little 5-minute talks that Andrew does about a wide range of their explanations of basic geotechnical topics mainly. normally illustrated with things like buckets of sand and so forth. So that's just something else he's added to bring alive some of the topic that we sometimes see as not a very lively one if we spend all our time looking at computers and so forth, but to see things actually happening makes a big difference. In his copious spare time, Andrew's also written a book about FEA, and I think the next slide might show the cover of this book. There it is, you can see. And I actually have a copy of it here. I mean, I don't know if it'll show up very well beside me here. Not really, does it? It's here. There we are. But Andrew told me I should read this book. So Andrew, I have read it, and I must say it's extremely useful because as giving a background to finite element analysis, it really covers a wide range of important topics. It's not written around any particular FEA program. It's general, which is also one of its very strong points. And in the rest of his spare time, Andrew also gets involved in the development of the Eurocode. I think he's on certainly one of the committees where trying to get a better understanding of using numerical techniques within that particular code of practice for geotechnical engineering, which is now being, I think it's on its second round of redevelopment. Anyhow, sorry, I've been going on for too long, but I think what's important, and I think what you'll soon be understanding, is that Andrew's title of his webinar tonight is typically challenging. Why is Geogrid so difficult to model in finite element analysis? And you might think, oh, it's easy. Anyhow, Andrew, it's now your chance to tell us all about it. So looking forward to hearing your webinar, and the floor is all handed over to you.
Well, thank you very much, Mike, for that marvelous introduction. So I hope I can follow it now with this presentation. Let's just get the slideshow started. Right, so you should see the first slide now, the title slide. Well, first of all, thank you very much to INA-IGS for the invitation to talk at this prestigious series of webinars that you've been running, a very successful series with a long list of prestigious speakers. So I'm honored to follow them with this 12th webinar. So entitled, as you see there, and introduced by Mike, why is Geogrid so difficult to model in FEA? So a title that might surprise some of you. According to the manuals that go along with these FEA programs, it is pretty straightforward to model Geogrid. So it might surprise you. So if you found it very easy to model Geogrid applications in FEA, then dare I say that might be something that you're doing wrong, because whenever I do it, I find it very difficult. I suspect that a lot of you have had similar experiences to me trying to model Geogrid in FEA and getting all sorts of issues, getting rather disappointed with what's predicted, finding it difficult to make it run. Some of those pictures you see on the slide there, they'll be very familiar to you. In fact, anybody that's used FEA, those pictures will be quite familiar to you. It's quite a difficult analysis technique to use. You need a lot of care with it to make sure it's being done correctly. So that's what I want to focus on, about the pitfalls of modeling Geogrid applications in FEA. So let's just have a quick look at an overview of what we're going to cover. So first of all, we'll have a look at the Geogrid models themselves. This is really the part that the manuals cover. So we'll just see how the Geogrid itself is modeled. Then we'll apply that approach to some typical cases. And then we'll see that how something appears to be missing, how we're not getting accurate predictions of prototype behavior. And I think that can be explained by a process known as mechanical stabilization. So we'll just have a look at what that is and how we simulate that in FEA. That's what I've been working on quite a lot lately. And then we'll revisit those typical cases by applying the new approach and we'll see what the result is. So it's useful just to make a distinction between two types of Geogrid applications. So I assume with an IGS audience, I don't need to go into what Geogrid is and so on. I assume that everyone's got some background knowledge of that. But there are many applications of Geogrid in civil engineering. The applications on the left are what we at Tensar are often called stabilization applications. They're applications where you have a granular layer with Geogrid horizontally within that layer, but predominantly a vertical load. So it's a vertical load perhaps from a piling rig or a crane in a working platform, or from a wheel on a road, or from a railway, applied to a granular layer with a horizontal grid. So essentially the load is at 90 degrees to the grid. So they tend to have either triaxial or biaxial type geogrids installed in those. And the other type is what is often called reinforcement applications, where the geogrid is more this type, designed to resist displacement force in one particular direction. So typical applications are slope reinforcement, perhaps for an embankment, maybe a load transfer platform, or a reinforced soil wall, or a reinforced soil structure, such as this. So we're going to look at two typical applications later on. One will be in this area, related to working platforms, and the other one will be a reinforced soil wall. Although this is called stabilization and this one reinforcement, we'll see that there's still an element of stabilization within these applications as well. And that's what explains sometimes the shortfall in the predictions of FEA compared to reality. So let's look at how Geogrid is modeled. So that if you want to model the Geogrid itself, what do you do? Well, all Geogrid goes into soil. So you measure the properties of the soil in the usual way, and you measure the properties of the Geogrid by testing it in tension in air. So you notice that you test the two materials separately, not together. And then in the FEA model, you introduce those two materials, and the performance is literally the sum of the parts. So it is the mechanical properties of the soil plus the mechanical properties of the geogrid, and that's how it is simulated. Now, this is the conventional approach, and this is what the manuals tell you to do. Now, regarding the elements used for the geogrid, then you use a membrane element. So that's an element rather like a piece of carpet. You can't put any compression into it. It'll just rock up. There's no flexural stiffness to it at all. It just has tensile stiffness. So when you pull it, then you get a resistance due to an axial stiffness, EA. So that's Young's modulus times the sectional area, but we never divide them up into the individual components because the cross-sectional area of a geogrid is not a uniform section. So we have to test it over lengths that incorporate sufficient repetitions of the geometry so that we get an overall stiffness expressed as EA. Now, even that on its own is quite complicated to come up with an EA value for a piece of geogrid. So just as an example, here are some EA values, just generic EA values for a particular reinforcement, uniaxial reinforcement product. Now we'll see that it depends on many factors, this EA value. First of all, it's the product itself. That's obvious. Different products are made of different polymers, and they have different geometrical characteristics and manufacturing characteristics, so they're all different. But even when you know the product, there is not one single EA value for that product. It depends on many further factors, such as the in-service temperature. So polymers behave they have different mechanical properties depending on the temperature. So you need to know the in-service temperature. So that's something else that affects the EA value. Also, the load level. So what's plotted in this graph is the EA value against time for the duration of loading for one particular product at one particular temperature, but you still have different EA values depending on the load level. That's because it's a non-linear stiffness. The stiffness actually depends on the load level within the grid. So the lower the load level, this is the lowest 10, we get the highest stiffness. So that's quite important. You can see that the EA value could actually double depending on the load level. In addition to that, the stiffness also changes with time due to creep of the polymer. So depending on the duration of loading, you see the EA value will also vary with time. So given all those factors that go into determining the EA value, it's not an easy process just to come up with an EA value. But there are different ways of taking into account all these factors. So that brings us to the constitutive model that you can use for the membrane element. So there are four main options typically available. The most basic is just linear elastic. So that is just one single EA value for the geogrid. So that needs to take into account the product, the temperature, the load level, and the duration of loading. So it's quite difficult to select just a single value that takes into account all those factors. But nevertheless, that is a method that is available. So if you plot load against strain, it will just be a straight line, such as that. If you think the load level is getting close to where the geogrid may rupture, you can adopt a linear elastic perfectly plastic model. So it's the same as the one above, but it will have a limit on the axial load that can be mobilized within the geogrid, above which it cannot take any more load. So any load within the model would need to be redistributed elsewhere. So that might be useful if you decide to do a ULS design of a geogrid reinforced structure. Option number 3 is a viscoelastic model. Now, this is the only one that will take into account the time-dependent creep behavior of the grid. So if you set up a reinforced soil wall, for example, and then you want to simulate its behavior over several years, for example, due to creep in the geogrid, this is the only model that will be able to take into account the changing stiffness with time due to creep or stress relaxation. So you can think of that in terms of it's similar to a linear elastic model in that you are selecting one single EA value no matter what the load level, and that takes into account temperature and the product, but over time that EA value will reduce. And the final option, this is the one I use most commonly. This takes into account the load level. So you remember the stiffness changes with the load level. Now you can see why that is, because it's not a straight line. You get a non-linear stiffness. So you can input this curve. So it's called an N epsilon, where N is the axial load and strain, epsilon is the strain. You can put in a non-linear profile for that. And it's called an isochronous curve because this is applicable for one particular duration of loading. So it doesn't take into account the change with time, but if you select one particular duration of loading, then you can use this curve. So that's what that is. It's an isochronous curve for one particular length of time of loading. Now, if you are going to use any of those models, you can obtain the parameters from the geogrid manufacturer. But that geogrid manufacturer will need to know all this information in order to give you these parameters. So it will need to know the in-service temperature that you expect, some idea of the product that you'd like to use, but perhaps they can advise on that, the duration of loading that you're interested in, and the approximate load level. You may not know all of this at the start, so it could be an iterative process where you have a guess at these values, do the analysis, and then when you know these answers, you can go back to the geogrid manufacturer and get revised values in response to these factors here. So that's the conventional way of modeling GeoGrid. Let's try that out on a typical application. So let's look initially at working platform type applications. So this is what I was calling the stabilization type application at the start. So there's a picture of a typical crane platform where we might decide to build a platform of granular material reinforced or mechanically stabilized with GeoGrid. So let's back analyze a plate load test that was performed in the laboratory to recreate a similar type of loading. It's smaller scale, of course, but it's a similar loading of a granular platform, 300 millimeters thick, with 2 layers of GeoGrid, a 300 millimeter square plate that you see there in the middle, over a subgrade composed of sand. So that test was performed. So this is the data that was recorded from the laboratory. So that one control was done without any GeoGrid, and we got this load displacement response. And with the GeoGrid, we see a much improved response, stiffer and stronger behavior. And you notice that quite early on, at quite a small displacement, there's already a difference between the two. So that will become important in a second. So tests like these are good to back analyze with FEA to validate your approach. So it's always good to have a control to compare with the GeoGrid. Then you know that you're getting the soil parameters approximately correct. So the solid line shows the back analysis using FEA of the control plate load test without GeoGrid. Then what we did is we added the membrane element to represent the GeoGrid using the approach just described, obtaining as accurately as we could the stiffness using the isochronous curves, the nonlinear stiffness approach for this particular GeoGrid product, and that was the result. Now, this is a typical first attempt at trying to model a GeoGrid application. I find rather disappointing in spite of all that care and effort to get accurate soil parameters and accurate GeoGrid. You see that the sum of the parts, the soil mechanical properties plus the GeoGrid, just aren't enough to match what is measured in the prototype. What you notice is that in fact, it takes quite a lot of displacement, about 10 millimeters of displacement, before you get any improvement at all. But certainly nowhere near the true behavior that we saw in the test way over here. And that's the fundamental issue with modeling the GeoGrid in this way, is what we're doing is we're mobilizing a tension membrane effect, as you see illustrated in this photograph here. In order for this membrane, this material here, to support the weight of this man in here, it needs to deform. It can't stay horizontal and support that weight. You need a vertical component of the tension in order to support this load here. So that's why we don't see any benefit until we get some displacement. So once some displacement has been mobilized, and by using update coordinates, so when you do this approach, don't forget to update the coordinates so that this tension membrane effect is taken into account. But we're not getting this immediate benefit that we saw in the prototype. What we could do is just increase the stiffness of the GeoGrid, and some people do this. You can perhaps find ways of justifying that. But one approach is just increase stiffness until you get approximately the correct answer. So that is one approach to go about it. But is that valid, that approach? Like this chap here, we rightly should be very suspicious of these approaches, just adjusting parameters until we get something that matches the result. Okay, the result looks pretty good here, and it's hard to argue against it, but has it faithfully recreated the mechanics of the problem? So as with all FEA, you need to be very suspicious of the output, even when it does appear to be accurate and matching the behavior in the prototype. Is it only working for that case? What if we do something slightly different? Is that still going to work? And is that a satisfactory approach, just to double the stiffness until you get the answer that you wanted? So we'll come back to that. But clearly, using the conventional approach isn't quite working satisfactorily. So let's move on to a concept known as mechanical stabilization, and we'll see if that can explain this this shortfall in the performance that is predicted by the FEA. So to illustrate what mechanical stabilization is, we've got these devices called Smart Rock that a number of universities have developed. This particular one was by Penn State University. So here you've got a real rock. That doesn't do anything special. That's not very smart, that one. But this one, it's 3D printed, and it's smart because it's got accelerometers inside on 3 axes. So that means that you know all the time how it's rotating in 3 axes, but also how it's translating in 3 axes as well. So if we put that into any experimental setup, we know what the individual stones are doing, not just what collectively the whole setup is doing. So this was put in the laboratory in a ballast box setup of half a sleeper or tie on a layer of ballast, with and without a geogrid placed within the ballast layer, a little bit below the sleeper. And then the Smart Rock was placed just off the edge, the end of the sleeper, just where the geogrid is. So one test with a cyclic vertical load applied. So we could see what the Smart Rock does without the geogrid and what it does with the geogrid, with the intention of seeing what the geogrid does to the aggregate. So this is the new way of thinking that that we're taking here. Instead of just looking at aggregate plus geogrid and what they do, what the sum of the parts is what does the geogrid actually do to the aggregate? Could it be improving the aggregate in some way? So you see the Smart Rocks placed in this example with the geogrid, and then the ballast was placed over the top, and this is the setup with 2 sleepers or ties and a beam, and a cyclic load was applied here, not for a long time, just sufficient to see any difference in behavior. So there's the output of the angular acceleration of the Smart Rock on 3 axes. So they're all plotted there, but they're all about the same. And you see over the 500 seconds, so there's about 500 cycles of load, you see how there's rotation and it actually increases during the test. That was the result without geogrid. And then with the geogrid, you see the remarkable difference in the amount of rotation in the Smart Rock. So the geogrid is having quite a fundamental effect on the aggregate, in that it's confining it. It's interlocking between the geogrid and the particle that resists its rotation. So what happens is that particles interacting with the geogrid are restrained against translation and rotation, as we see here. And we also see that through interlock between other particles, this restraint is actually transferred up through the layer. So we get a layer of mechanically stabilized aggregate that extends about 30 centimeters above and below if we have aggregate below the grid. That creates a mechanically stabilized layer. Now, from your fundamental soil mechanics, you'll know that if you restrain particles against rotation, that significantly increases the shear strength of that aggregate. It's for the same reason that an angular aggregate is stronger than a round aggregate. because angular particles interlock better and it's harder to rotate them. So we get an even more enhanced effect here. So we should see a higher shear strength of this material because the particle is resisted against, there's resistance against the particle rotation through interaction with the geogrid. Now, never forget that in FEA, you are modeling the soil, the aggregate, as a continuum. So it does not recreate this effect. Even if you model the geogrid as individual ribs, which I've seen some researchers do, that's still not going to recreate this effect in a continuum. Only perhaps by using DEM, discrete element modeling, which is actually modeling it as a particulate medium, you may recreate this effect. But in a continuum, you have to put this effect into the parameters, into the input parameters for the material. The FEA will not do this on its own. So what we then did, we were searching for this higher shear strength that should occur within this aggregate material. So instead of testing soil and geogrid separately, as you saw at the beginning, why not test them as nature intended together as a composite, to see how they truly perform together and to see if the geogrid actually improves the aggregate. So in large triaxial compression tests, so 0.5 meter diameter by 1 meter high, so they need to be that big because of the large aggregates that we are testing. We tested aggregates on their own without geogrid, and then we placed a layer of geogrid within the specimen, usually at the mid-height, sometimes multiple layers, but more usually just with a single layer. And then what we're measuring, instead of non-stabilized soil plus geogrid, we're actually measuring mechanically stabilized soil properties as a composite. And what we see is higher strength in this area here around the geogrid plane, and it reduces as you move away from the plane until you get to the full influence extent of the geogrid, or at least about 30 centimeters, where the properties then return to the non-stabilized soil properties. So we developed a constitutive model to recreate this effect because there wasn't really a constitutive model available that would model this behavior. So I'm just going to show you how the fundamental distinguishing features of this model. It's plotted in here in principal stress space because that's how the model is formulated. So we start off with a frictional component of strength here. So this has a slope K naught. That can be related to the friction angle, but it's not the actual friction angle because this is not more stress space. Then there's a non-linear envelope for the non-stabilized material because even dense aggregates without geogrid still have some non-linearity due to dilatancy. So you'll see that anyway. But it's not a true cohesion. It does, in reality, curve down to the origin. If you use a more Coulomb model with a cohesion intercept here, you get a reasonably good approximation. So when you have a linear failure envelope, such as the more Coulomb model, you can only use this dashed line here. Well, that's reasonable for this material. But when we add geogrid, what we see is a very much enhanced effect of interlocking and dilatancy due to the presence of the geogrid. So we get a higher failure envelope at the elevation of the grid. So the geogrid is at this elevation. So at this point in the stabilized soil, we're getting the maximum strength. So we get a very much more non-linear failure envelope. That's defined by this asymptote, which is similar to a cohesion called CT, and the line reaches this eventually as an asymptote, but it does curve down to the origin. Now, trying to use the more Coulomb model here would be more difficult because it's very non-linear here. So that's why we developed this model with this non-linear failure envelope. So typical applications are quite low stress levels because they're quite near the surface. So it's difficult to fit a linear failure envelope to this red line. It's reasonable to the black line, but not to the red line. And the other distinguishing feature of the model is that it will vary the strength depending on your location relative to the plane of the geogrid. So when you're at this point in the mesh, you're on the red line. As you move away, the strength envelope is interpolated and will eventually come down to the non-stabilized line when you reach the full influence extent here. So two distinguishing features of this model are the nonlinear failure envelope and its variation. Its variation with elevation above and below the grid. So this area here represents the additional shear strength from mechanical stabilization. So it provides a means of actually measuring this mechanical stabilization. And this constitutive model is called the Tensar stabilized soil model. And it's been implemented into Plaxis, FLAC, Abacus, and CSAR softwares. So that's been a big advance in the field of the stabilization function from Geogrid. We have a way of measuring it and of simulating it in FEA now. And you see that we can't do this by the traditional membrane element and plus soil. In fact, with this one, we don't use the membrane element at all. We don't even have the geogrid element in here. We just model it as a composite. If you want to read more about it, this was developed a couple of years ago. I co-authored this with Johan Clausen while he was at the University of Aalborg in Denmark. So that paper's available if you want to read more about it. So let's see that model in action by simulating one of those large triaxial tests. And actually, this is how we derive the parameters. We back analyze the tests. It's quite difficult to obtain each of those parameters individually. So we back analyze a series of tests in order to fit the parameters to the results. So here's a 2D axisymmetric FEA model of one of those triaxial tests. So if we have geogrid, then it's at the mid-height elevation here. We don't model the geogrid element itself. We just input the elevation and we input the influence extent here. So we adjust that to fit the results. That's one of the unknowns that we determine. So let's see the output of those analyses. Back analyzing these triaxial tests. This is a well-graded crushed rock without geogrid at the moment. Now the gray lines are the laboratory data. So I've plotted it as load in kilonewtons per radian. This suits more the FEA output against vertical displacement. So we get these typical hyperbolic curves for triaxial testing that you see here. These are at 3 different confining stresses. That's why one goes above, they go up in series. The quite low confining stresses, because it's very large, we use a vacuum to apply the confining stress. So it's not a conventional triaxial cell. So the gray is the laboratory data. These are unload reload loops. Okay, we don't need to worry about those for now because these models don't have a hardening facility, so it would not recreate that unload reload loop. And also it's linear elastic, perfectly plastic, so we get straight lines here and then perfectly plastic behavior here. So we're trying to get a reasonable match with the pre-failure deformation and then a good match with the failure load. So we're getting pretty good at all 3 tests with one set of data using the new model. This is without geogrid so far. This is the more Coulomb model. It is, in this situation, they are virtually equivalent because they're both linear elastic, perfectly plastic models without any geogrid. So we get similar behavior in the more Coulomb model. I just put those red dashed lines there just to show you the failure loads of about 7, 9, and 13. But you'll see why on the next slide. So that was without Geogrid. This is a test on the same crushed rock with the stabilizing Geogrid at mid-height. So we get much higher strength, you notice. Before we were up to about 13, now we're up to about 18. So higher strengths due to the Geogrid. And by specifying that in the parameters where the Geogrid is and the influence extent and the other parameters, you see we get a very good match with the failure load because we're getting that extra benefit. But this next graph is the most interesting one because this is with the traditional approach. This is with the more Coulomb model plus the membrane. So this is the way the manual tells you to do to simulate Geogrid applications. And we're using as realistic a curve as we can, the nonlinear n epsilon curve. You see we don't get anywhere near the failure loads. In fact, if I put those dashed lines in, remember those were the failure loads for the case without Geogrid. You notice that the soil is failing at about the same load because the soil doesn't know that it's got any extra strength from mechanical stabilization. It's got the same strength parameters as before, so it actually fails, even though you've got the membrane element in there. Then what happens is due to tension being mobilized in the membrane, you get a slow increase in the vertical load. But you're not going to get up to here. If you increase the stiffness very high, you could get the line to go up like that, like it did for the plate load test. But that's not recreating the fundamental mechanics of the problem. So you see the sum of the parts just isn't enough. The true performance of the aggregate with the Geogrid is greater than the sum of the parts because the Geogrid is actually improving the aggregate, and you need to include that effect in the model. So if we go back to the plate load tests that we saw before, and our friend here was rightly skeptical about doubling the stiffness. If we try the new constitutive model, a TSS model as we call it, Tensor Stabilized Saw model, there we get a much more accurate fit. We're getting more of the curvature that we saw before. More realistically, it's continuing to approach a plateau of eventual failure instead of just rising and rising in the case of a membrane element. So it's an example where we've also got a good match with the data, but I think we've more faithfully recreated the mechanics of the problem there. Yes, so he's happy with that, good. So, so those are the stabilization applications. Let's move over now to reinforced saw walls. I'm sure you're all familiar with those. There are a couple of examples. So these are walls with layer upon layer of Geogrid extending back behind the wall and mechanically stabilizing or reinforcing the fill that's added behind. So you can support near vertical faces such as this using these types of Geogrid, reinforcing Geogrid. Now, before I go into the mechanical stabilization part, I thought it'd be useful just to give you some of my top tips for modeling reinforced saw walls. If ever you've tried to do this, you may have found it rather difficult. Actually, particularly reinforced slopes. I've sometimes tried to simulate reinforced saw slopes that limit equilibrium methods show are stable, and I can't even get the FEA model to stay up to support the thing. It's quite challenging to model these structures. So here are some just general tips from my own experience of modeling these types of structures before we get into the mechanical stabilization part. The reason I've got this mesh here, you'll see in a moment, I'm recreating a laboratory trial wall That's why it's got these limited dimensions here. So a few tips then from me, backfill model and parameters. So the fill material here, that needs quite an advanced model to get realistic output. If you just use a basic linear elastic, perfectly plastic, more Coulomb model, it's going to be difficult to get close to actual results, even more difficult than usual. Because there's a large stress change during construction from placing this layer to then placing all the layers above, you get quite a large stress range here. So it's better to have a model that will have a stress-dependent stiffness to take that into account. You also get a lot of yield. So you need realistic prediction of yield deformations, not just elastic, because at these low stress levels, you get quite a lot of displacement. You need, of course, frictional strength. So good models to use are hyperbolic models such as Duncan and Chang or the hardening saw model. So they're particularly well suited to these backfill materials. Now, regarding wall elements, you've got a choice of using area or volume elements in 3D or just using line or surface elements. Of course, it's easier to use line or surface, but how accurate is that? Well, generally in soil structure interaction, this is considered more conservative because you're losing the effect of the moment effect of friction on the back. When you've got a thickness here, the soil friction on the back of the wall helps actually to reduce deflections, but you lose that benefit here. So it would normally be conservative, but you've got the joints in the wall facing, which makes it particularly challenging. So walls are made of panels or blocks, so they're not a continuous structural member. So you could put hinges in here, but then it'll probably be too conservative if you do that. It's a bit complicated because normally when the wall is sufficiently high, you've got enough down drag and compression in here that this will act like a continuous member because the whole thing is in vertical compression, but that won't necessarily happen early on. I found a good way that's worked sometimes is if you put a hinge just at the base, at the toe of the wall, then that works reasonably well. But to be more certain, it's better to use the actual area or volume of the blocks or the panels. It takes longer, of course, but that will be more accurate. Now, interface elements. That's often a tricky one with these walls. Where do we put interface elements? Here's a deformed mesh, exaggerated 5 times just to help see what's actually happening. And this is close up from somewhere in here. So we can have a look at what's happening. So I found what you need to do is, yes, you need interface elements on the back of the wall because you could tend to get a lot of settlement of the backfill relative to the blocks because the blocks are much stiffer than the soil. So you see this node here in the soil was up here. So you do get quite a lot of movement. So that's probably the most important interface element on the back of the wall. You need them between the blocks as well to model that. As I said before, when the wall gets higher, it's all in compression and it's not so important. But early on, there could be some movement between these blocks when there isn't much self-weight. Be careful with the connection between the geogrid and the block, because if you're putting interface elements here, if you're not careful, the geogrid won't be connected to the block. So just be careful with that. It's a good idea to extend it along here just to make sure that it is connected. And then where people often think about interface elements and want to use them is between the geogrid and the soil. But I found that at serviceable strain, so if you're predicting deformations, it's probably not necessary because you've got the interlock between the aggregate and the geogrid apertures. So there won't be any sliding, any significant sliding between the aggregate and the geogrid. So actually here, I don't use an interface element at serviceable strain levels. If you wanted to use it for ULS design, for internal strength, then maybe you will, but that's quite a big task. I'd still recommend just using limit equilibrium for ULS internal failure in a reinforced soil wall. It's still rather complicated to use an FEA for ULS design, except for overall stability. Of course, you can use FEA there, I find. Now with the construction sequence, you can build the whole thing in one go if you want, but that won't be very realistic because all the stress states will be wrong and the displacements will be wrong, because you're getting more displacement at the base early on as you build up the wall. So you need to build up layer upon layer. You don't necessarily have to do every individual layer. You may be able to do them in groups and still be reasonably accurate, but it's important to do that layered construction in order to get the correct predictions. And when you're doing that, don't forget in the displacement output, you need the displacement only after the element has been activated. If you don't do that, you'll get a big over prediction of the wall. Over prediction in some way actually depends what's happening. Sometimes it rotates, so you might actually get large negative values at the top. This happens because when you place a new layer, because of nodal connectivity, this block, when I place it, the displacement needs to match the displacement of this block if there's connection here. So when this is activated, it already has a displacement associated with it, but that's not realistic, of course. It can't displace before it's been activated. So there are options in the output to remove all those displacements that occur before an element is activated. So don't forget that. Right, let's go back to mechanical stabilization. Now, to illustrate this, I'm using back analysis of an interesting series of laboratory trial walls, but full size, that were constructed at the Public Works Research Institute in Japan back in '95. The backfill was a silty sand, heavily compacted, hence the quite high phi value that you'll see on the next slide. And the geogrid in this example was an older product, a Tensar SR55 reinforcing geogrid. It's quite similar to the reinforcing geogrids that are used today. You see it's a 6 meter high wall with 6 layers of primary geogrid and 5 layers of secondary in between. Quite a large spacing of 1 meter spacing for the primary geogrid. And displacement sensors, pressure sensors everywhere, but we're just going to focus on the displacement measurement for now. Now, looking at the fill material, from previous back analyses done by other authors and by other data, it's had quite a high friction angle of 45 degrees, but no apparent cohesion. Then from the triaxial testing that we've done on similar sand, from biaxial testing that's been done that I don't have time to present, as well as back analyzing this particular wall, we estimated what we think the stabilized strength is of the aggregate of that sand in close proximity to the geogrid. That's the red line. But the problem we have with this non-linear failure envelope is we really need to use a hyperbolic model, such as Duncan and Chang or hardening saw model, for realistic modeling of the backfill, as I described earlier. But the TSS model that has the non-linear failure envelope is linear elastic, perfectly plastic. So it doesn't have all those benefits of that hyperbolic model. So we needed to do a little trick. What we did is we created 2 models so that they fitted, each one fitted this failure envelope for a different stress range. So when sigma 3, the minor principal stress, was less than 20 kilopascals, we use this failure line, which is very close to the red line. And then when sigma 3 was above 20, we use this line, which is also very close. So it fits very well to that curve. if we do two separate straight lines. So it's a way of making a linear failure envelope match the nonlinear. And you notice that above here, it has the same friction angle, but a higher cohesion intercept, whereas this one has zero cohesion, but a higher friction angle. So that's how we represented the stabilized material. So then here's the mesh for the trial wall. It was built in a pit. So there's with a frictionless back here. So that's why we put a roller boundary here, and it's on a rigid concrete base. So it's not a typical wall, but quite well-controlled boundary conditions. So we modeled geogrid in this case. So for reinforcing grid, we do include the geogrid elements because it's necessary to connect to the facing. So we have the primary and the secondary grid, as you see there. Here's the reinforced fill with no stabilization in orange. Now, because the geogrids are quite widely spaced at 1 meter, the geogrid influence extent does not go all the way between the grids. It goes about 30 centimeters above and below. So we have a separate zone of mechanically stabilized fill shown in red. And that's represented by the high friction angle material because sigma 3 was less than 20 in this area. Only down here towards the end of construction did sigma 3 actually get above 20. So this green zone represents the upper failure envelope with the higher cohesion, but the same friction angle of 45 degrees. Now there's a bit of an iterative process here. You need to run the analysis to see what the sigma 3 values are in the output, and then go back and specify these zones so that you can specify where the two failure envelopes are valid. So this would start off in the red zone early in construction, but when there's significant overburden from the soil above, then it switches to the higher sigma 3 value. Quite a complicated process, but it's a way of getting all those effects of nonlinear stiffness and a nonlinear failure envelope all in one FEA. So let's have a look at, now this is how we model the geogrid. Yes, don't forget the geogrid. Use the, because it was a laboratory trial, it took about 6 days to construct. So we took a 6-day isochronous curve at 20 degrees C, and that's the N epsilon plot that was used to specify the geogrid stiffness. So let's look at the results. So this is the measured data from the trial. So at the end of construction, that's what EOC is. So the good thing about a trial wall is you can actually measure the displacement during construction. That's difficult to do in a real wall. So we're getting up to nearly 30 millimeters of movement, horizontal displacement of the facing during construction. When we simulated construction using the conventional approach, so no mechanical stabilization of the fill, just fill plus geogrid in the conventional way. You see, as is so typical, if ever you've modeled, if you've ever tried to back analyze a monitored wall, you always get over prediction of displacement. So we're getting about 30% over prediction, nearly 40 millimeters predicted in the FEA as opposed to less than 30 that was measured. When we add the effect of stabilization, using that approach with the two failure envelopes, then we get a very good match. So it's a plausible way of measuring, accounting for this missing link in the performance of geogrid applications. But other authors have back analyzed these walls using FEA. And one paper gets very good results by taking a higher stiffness of the geogrid. Now, we've seen that before. Justified for various reasons. And you see also, you get a very good match with the test data. So that makes it hard for me to argue that our way is better than their way when they both seem to give exactly the same result. This is a drawback of FEA. There are so many input parameters. There's usually more than one way of skinning a cat, and you can get the result that you need. But there was something very interesting about these trial walls that allows us to to simulate something else and find another way of validating this approach. The trial wall had a trick up its sleeve. During construction, they installed heating wires around the geogrid so that after construction, they could effectively cut the geogrid. So after construction, they began the cutting process, starting at number 1, cutting the top layer here, then here, and down to here. And they started up here, 7 down to 12, 13 down to 18. They just kept cutting and cutting the grid, shorter and shorter, all the way to 48, then 49. They started coming back up this way to 55, and then up to here. You see how remarkably short the geogrid became, and the wall was still standing. It only collapsed at the last cut here, 60. Now, the very interesting thing about this is that when the geogrid is cut, you lose the reinforcing benefit. No longer is there a connection between the geogrid and the facing. So all reinforcing benefit is lost. But the geogrid is still within the fill. The aggregate is still interacting with the geogrid, so you're still getting mechanical stabilization. So this provides a very useful test to back analyze, to look exclusively at the effect of mechanical stabilization with reinforcement effect removed. So let's go back to these graphs, and this is the displacement just before failure. So they measured the displacement out to here, which by coincidence was close to this earlier non-stabilized end of construction prediction. Now, by using our stabilized approach and getting all the way to cut 51 just before it failed, we get a very good agreement with the displacement data. Something else we looked at, and the good validation of the approach, was to look at the development of maximum wall deflection during the cutting sequence. So with the non-stabilized end of construction simulation, you see 38 millimeters corresponds with the 38 here, the maximum value. And as we cut the geogrid in the FEA model, so we just created gaps in the geogrid, you see how the displacement increased, and then we got failure at cut about number 43, that looks like. When we try the approach with the higher geogrid stiffness, which gives a very good prediction of end of construction, you see the higher stiffness does not help when the geogrid is cut. It eventually fails at about the same cut. Still a long way from the true point of collapse at cut number 60. If we take the stabilized approach, this is the only one that both has a realistic prediction at end of construction and actually allows the wall to stay up for longer during the cutting sequence to a significantly higher number of cuts, not quite to 60, but certainly a significant increase there. So that makes it a very useful back analysis, because it gives us two bites of the cherry, if you like. We can back analyze the end of construction, but we can also back analyze this cutting sequence. And only using mechanical stabilization were we able to get a realistic simulation of both of those. So it's quite powerful evidence of this mechanical stabilization benefit within the wall. If you want to read more about it, this has all been written up in a paper published in the Transportation Research Record quite recently that I co-authored with a promising young researcher by the name of Michael Doby. So you can get hold of that and read more detail about that approach. So that brings me to the conclusions. So you saw under prediction of performance without modeling mechanical stabilization. So this is the fundamental problem that I have found, and I expect many of you have found, that whenever you try to model a geogrid application, it's under predicting performance. Other authors, researchers rather, have tried things such as increasing the geogrid stiffness. We saw how that sometimes works, but it does not appear to faithfully recreate the true mechanical behavior. The only way that that seems to be done is by taking account of mechanical stabilization, because the strength of the soil and the geogrid is definitely greater than the sum of the parts. You can't just measure them both separately and put them together in the FEA model and expect that to give you a realistic prediction. Only the enhanced shear strength, the actual improvement of the strength due to interlocking of the granular particles with the geogrid. So you need to think about it at a granular particulate level to see what the actual behavior is. And that's not being done automatically by FEA, which is a continuum. It doesn't take into account particle geogrid interaction effects. So what are the implications for design? Well, reinforced field strength is critical even for deflection. So that might not be appreciated by some. For deflection, you tend to focus on stiffness. But actually, in many applications, particularly reinforced soil walls, where there is a lot of yield of the soil, a lot of permanent deformation, then the strength of the material is very important. Now, often when we do a design of a reinforced soil wall, we're very conservative with strength parameters for the fill material. And rightly so in some situations, because because fill materials vary. It's not something we can measure the strength of before construction. So in the ULS design, you can justify taking a conservative approach using lower strengths. But all too often, those low strengths for ULS design are transferred to the SLS design. So when you do an FEA to predict deformation in a reinforced soil wall, because the strengths are very low in the first place, plus you're also missing the mechanical stabilization benefit, all too often very high deflections are predicted, and they're just not realistic. It's much more realistic to be optimistic rather about the strengths for SLS design, not the ULS design. But if you're going to predict deformations, use a higher strength and also a mechanically stabilized strength for the SLS design, and then we're going to get much more economical designs. And unfortunately, on many occasions, the reinforced soil option is rejected altogether, sometimes on the strength of FEA results because they show too much deformation. And that's a real pity because it was probably being modeled unrealistically. A lot of the benefit from the geogrid was not being included. So that brings us to the end. Thank you everyone for listening, and I'd be very pleased to take any questions through our moderator, Mike, that have been received.
Well, Andrew, thank you very much for that presentation of, I think, some fascinating data. If people have not seen these aspects of researching into a technique, I think you would have seen there's a lot to it, and I think that's really what's behind the title of the talk today, and why Andrew used that title. And yeah, so far we don't have many questions, but I mean, actually I have one or two myself, but But we do have two from Yara Franco, and I'll read them to you, Andrew. So, hi, Andrew. Thank you for the webinar. In the modeling of the PWRI trial wall, the geogrid was inserted in the model as well, question mark, or as an independent element, question mark?
It was modeled in the conventional way as a separate membrane element, but in full contact with the soil, no interface elements. Yeah, so when we're using the triax or biaxial grid, then we do not include, rather when we're using triax stabilizing geogrid, we don't include the geogrid in those applications where we have a vertical load and a horizontal grid. But in reinforced soil wall applications, we do include the geogrid because it needs to be connected to the facing. It's important from that aspect. Yep. Okay, I hope I answered that.
Well, we have a follow-up question from the same person. What about fine-grained soils? Would the model be applicable for those as well?
Good question. Haven't really looked at that. Yes, you're right to raise that. We shouldn't just apply that. It may well not work, or there may be a reduced mechanical stabilization benefit in fine-grained soils. But we just haven't looked at that in detail yet. So I would recommend not using it in fine-grained soils for the time being, certainly, until we or others have looked at it further.
I think that's the sensible advice there. From Nicholas Denise, could you please come back on your explanation about the way that you have considered progressively the displacement output regarding the reinforced fill structures, and explain once again, thank you very much. You might want to read that yourself, actually, Andrew, that question.
No, I understand. Yeah, well, when I was preparing this, I thought, yes, some more explanation might be useful. So with some images, but I was sort of, it was too tight on time. I don't think I've got anything ready, but what I'll do is I'll skip back to that that slide. And just try to explain again.
You'll need to reshare your screen.
Oh, it's gone out, is it? Sorry about that.
I don't know if we can ask Reefer to.
I can do that.
You can do, okay.
Okay. Right. So you should see that now. This is where I was explaining it in before. I don't have an appropriate diagram to explain it, and if we were in the room, I could just draw it on a whiteboard, but I'm not going to try and attempt that now. It's probably possible if you know what you're doing. So let's use the example of this layer being added here. I'm assuming you can see my cursor. So when you put the lower layers, these layers will displace. So there'll be a displacement here, let's say, of 5 millimeters at the end of this construction stage. At the next stage, when you activate these elements here to simulate the next layer, when you put this layer on, this block is already going to have 5 millimeter displacement associated with it because of nodal connectivity. It must be connected to the block below. And that effect accumulates. So by the time you get up to the top, when you activate this element, it's already got a displacement associated with it because it's connected to all the elements below. But it's unrealistic because in reality, it can't displace until this actually exists in real life. So when you go to the output of an FEA, if you just plot total displacement, which is the default displacement, you'll get unrealistic predictions. you need to subtract the displacements that were caused in these elements before they were activated. So the programs, I think most of the softwares do this automatically. There is an option to do that. I always hesitate to refer to specific softwares, otherwise I'll be promoting some, but it's in one popular one, it's called sum phase displacements, something like that. So it's adding the displacements that occurred in the phases when it was activated, not before. Okay, I hope that helps.
No, thanks very much, Andrew. We have it's a very interesting question here from Ian Williams. It says, very interesting, thanks. Have you looked into whether the mechanical stabilization effects of the geogrid might be captured in traditional constitutive soil models by enhancing the soil dilation as a function of perpendicular distance from the geogrid? It strikes me that such effects combined with additional confinement afforded by the geogrids may be physically realistic, a physically realistic representation of what happens in the field and might therefore replicate field performance. So that's trying to reuse models in a different way. So what's your thought about that, Andrew?
I think in the early days, we did look at things like that, adjusting different parameters, such as dilatancy, Poisson's ratio, things like that. It was difficult to get any of them to have the effect that we needed, to have sufficient effect. So I'd love to be proved wrong. If anybody else wants to look at it, I'd be skeptical whether just manipulating dilatancy alone would have the effect. It may also have other undesirable effects trying to get the analysis to run. So if you're going to increase dilatancy, are you going to increase the friction angle as well? You can't really do that because in reality the friction angle varies with the stress level, so that would be quite a dangerous thing to do. So if you increase dilatancy alone, it may have some effect, but perhaps not enough. And then you got issues with increasing non-associativity, so that often causes issues within an analysis, trying to get that to run. So short answer is we might have looked at it briefly a long time ago, but I'd be very interested to hear if anybody else looked at it.
Sounds like a good challenge. Next quick, we have actually the questions are piling up here, Andrew. I hope you've got some spare battery left there inside you. But yes. So from Arimas Suxia, sorry, slightly different name. Hello, Andrew. Nice presentation. What about the situation if the manufacturer of the geogrid is not able to give the required parameters of the geogrid for the FEM analysis? Maybe it is possible to model the geogrid performance via the soil parameters. Oh.
Yeah, I'm not quite sure what application is being considered there. I mean, in stabilization type applications, as we call them, working platforms, roads and rail and so on, then I mean, that is what we're doing. We're not putting in the geo properties, we're putting in the properties of the composite. So that works. To obtain those parameters, though, you can't guess at them. I mean, you need to actually measure it. So you could measure it in a large triaxial, or you could measure it in some full-scale test setup, maybe a large plate load test, whatever is suited to your application. If we're talking about reinforced soil walls, yeah, I've tried it, but the issue is with the facing. You need to find a way of getting that supported. So even if the mechanical stabilization were the dominant function of the geogrid, you still need some reinforcement to just support the facing. if you remove the geogrid, then you've got that problem. So it's tricky in those applications.
Yeah, okay, yeah, no, thanks. Yeah. Right, further question. This is now from this is from Professor Wijoyo. He one of our previous speakers, actually, also the chairman of our local geotechnical society. I find that extrapolating the lab test results to actual wall performance would be quite challenging. Would that be the case for your research as well? And the second question, would the MS model, the one that you described, be applicable to sandy fill materials? My understanding is that the MS model would be applicable to rather large pieces of fill material only.
Okay, thanks for those questions. So using this approach, we've already back analyzed several full-size monitored walls, at least 3, and we got very good results. We're hoping to publish that soon, aren't we, Mike? So we have already taken this approach to full-scale walls, and it seems to work. Regarding mechanical stabilization in sand materials, we've tested down to what you might call sandy aggregates, sort of a coarse sand, fine gravel. We still see a surprising benefit. So I don't think, the mechanical stabilization certainly diminishes a little, but we still see a significant benefit, even if the particle is much smaller than the aperture of the grid. Just those particles still interacting with the geogrid do get a benefit. So I would suggest that any material that behaves in a granular form, in a granular way rather, will get benefit and could be modeled in this way. That's my experience. When you get into fine-grained soils where the behavior changes quite a lot, then probably not, but we haven't looked at that. But the performance in sands is still remarkably good.
I think an important comment there, Andrew, is that, I mean, you have to do the testing, whatever the soil types you're looking at.
Yes, of course. So we test each specific aggregate with each specific geogrid product. We never approach this as in design, certainly not guesswork, but also when we back analyze projects, we spend a lot of time trying to get the test data from each case, if not trying to recreate that aggregate and doing the testing.
Oh, thanks, Andrew. Okay, from our first questioner, Yara Franco says, thank you, Andrew. So we'll then move on to the next question. Arif Matandong, this is in Indonesian. I'll do my best to translate it for you. So in design of reinforced soil, the geotechnical data is important. And how accurate if we use correlations because the data is minimum. So what about the accuracy of correlations when you have minimal data in this kind of situation? It's a very general question. It's not specific related to what you've been talking about.
Well, yes, correlations, of course, will be getting very approximate. I assume it's more for the fill material. Maybe you don't have the test data there. I mean, even if you do test the fill material, there's still uncertainty there because you're not testing it in its actual installed compacted state. So you just need to use engineering judgment, just like in all geotechnical engineering. The greater the uncertainty, then the more conservative you need to be with the design. So it would be difficult to start doing FEA with parameters based on correlations. I think you just have to be very conservative. You could use it broadly to help understand the problem. I wouldn't use it as a design tool on its own to make predictions that you need to rely on. You can use it just to help understand critical issues in your design. So FEA is very, very good at that, in that you can change things and see what's important in the design. And for that, then yes, estimated correlated parameters may be sufficient.
Yeah, I think yes, it's the importance of site investigation. I'm afraid. I mean, it's not only in Indonesia, but in many places, as we all know, we get asked to do designs with next to no data, or maybe zero data altogether, which is not the best way to go. But inevitably, we're going to have to be conservative. So, next question from Gali Rio Prayogi. What about the use under rigid pavements? Thank you. I think of the mechanical stabilization model.
Under pavements, then we're talking about repetitive loading, presumably. So then it's not straightforward. You could use the model to assist in predictions and simulating the behavior, but then you've got to add the effect of repetitions of loading on a pavement. So, I mean, it depends what you want to analyze. If you do want to just simulate the application of a monotonic load on a rigid pavement, then yeah, it should work. I haven't tried it personally, but there's no reason why it shouldn't work in that situation. But if it's for road design, then you have to add in the accumulation. So you might take a mechanistic empirical approach using the TSS model to predict permanent deformations under a single loading, and then add some sort of empirical multiplication of that effect for repetitions of that loading.
Oh, thanks, Andrew. Yeah. Okay, our next question is in Indonesian again. Johnny Bahru. Seberapa tahun? So how many, I think it means years, can you use Geogrid in retaining walls to do with the taking into account loading from traffic vehicles? I think that's a very general one. I'm not sure it's specific to what you've been talking about. I think we'll move on to the next one, Andrew. Next one is from Pak Go Chi Leong. Interest. So Pak Go, he was the previous president of our Indonesian IGS chapter. He's also very heavily involved in a piece of software that you know pretty well as well. He says, what about if we model first the internal stability of the MSE wall system, making sure it is stable? Then the second step is to consider the wall with an equivalent strength of the composite material, Geogrid plus backfill material as a composite. So I think what's there is taking that block of reinforced soil and giving it some parameters that match a previous internal analysis. So what do you think of doing that, Andrew?
Yeah, that sounds plausible to me. I mean, I've sort of hesitated to look at internal stability using FEA because I still think it's really difficult. And if you're going to do it in design, there's a risk that I think you might miss something. Yeah, you might get something that's important that's not captured. And so the limit equilibrium methods are well established. So I still recommend using those in everyday design, unless it's something particularly unusual that is not suited to limit equilibrium models. So I tend to use FEA just for deformation prediction, and then take this approach of modeling effectively everything, the geogrid plus the effect of mechanical stabilization on the aggregate plus the surrounding ground to capture settlements and maybe overall stability. But in a detailed study, yeah, I could see that working. I mean, there are details to work out there, but yes, representing the detail of the internal structure of the wall first, and then somehow as a composite block sounds interesting. Yeah.
I guess probably most relevant to the external stability analysis rather than you've essentially dealt with the internal stability, I guess. So it's really looking at everything outside it.
Yeah, I've done external stability using FEA, even 3D FEA. But I didn't take that approach. I actually modeled it in the conventional way because it was purely for external stability. There was no need to look at the detail. But if I wanted to look at the detail of the deformations as well, then I think if the FEA geometry is already there for the wall, then I would just use that model, the same model, to do external stability and the deformations, the internal deformations.
Okay, thanks very well. I think we got to I think we can handle a couple more of these questions. The organizers will tell me when the time is running out, but this is from Hugh Nguyen. Sorry, I'm not very good at those Vietnamese names, but hi, Andrew, very interesting presentation. If the project is built under variable temperature conditions, how will the Geogrid model be affected? This is an interesting question, that.
It is. I mean, you may be better place to talk generally about that. I mean, the FEA constitutive models that I talked about would not be affected because they don't take into account temperature. I mean, there may be such models available, but the main models that are used and the ones I presented, you would simply have to select the stiffness value appropriate for one particular temperature. If you wanted to look at time-dependent effects, I guess you could manipulate the viscoelastic model to relax more in higher temperature and try to see that effect. But it's not something I've tried, so I can't give you the benefit of any experience of trying it myself. Yeah, but that's as far as I can go on FEA modeling of that. I don't know what you do in conventional design, Mike, when you got variable temperature.
Yeah, well, I'll make a couple of comments. I mean, we can, in limiting equilibrium approaches, then if we use the right techniques, we can associate different sections of a wall with different temperatures. And one common question is, if we're in hot countries and we have the sunshine right on the, say, on the front of that wall, we can see in the cross section there, will that affect the strength of the, say, the first meter of geogrid because it's being exposed to higher temperatures? And the answer is, well, it could do. So we can, in some models, assign a different temperature to, say, the front 1 meter of the geogrid, and then take it into account in the limiting equilibrium analysis. But of course, that's only going to look at failure, and obviously not look at the deformation effect of that temperature difference. So yes, it can be done. Yeah, let's just move on. Oh, sorry, Andrew. Yeah.
Well,
yeah.
Since you mentioned that the variation geometrically in temperature, then yes, of course, you could represent that in FEA. Maybe that's what the questioner was intending. So you could put in a different stiffness near the facing and then a higher one further into the soil.
Yeah. Okay. Yeah. I think so. I mean, I think that would be one possible approach to that issue. Yeah. We have Raina Warbes. Hello, Andrew. Thank you for the interesting presentation. The question on my side: how would you handle deformations, membrane effect, or other large deformations of the geogrid in pavement and working platform applications, especially in FEA? This is leading to big problems in back analyzing model tests. This seems kind of relevant to what you've been talking about.
Yes, if you want to recreate the tension membrane effect, then you just need to take the update coordinates option. Otherwise, you won't get the tension membrane effect. But what you'll find is that you need large deformations to mobilize that effect. And that's one of the problems that I was discussing. So when you back analyze a field test, you'll see that you get much better performance in the field than by simulating in FEA the tension membrane. So missing link appears to be the mechanical stabilization. So if you can put that into the model, then you should get more realistic outputs. But you need to have the test data for that particular aggregate and the particular GeoGrid product. You need to take a different approach, which is test them as a composite material and characterize them as a composite material instead of the aggregate plus the GeoGrid. So that, that's the problem with that approach. The performance is greater than the sum of the parts. The grid has an effect on the aggregate that you need to take into account. Yeah.
I mean, your modeling techniques have allowed us to do that, and I think that's a big step forward. Because I think in my experience over the years, people have always suspected that this was the case, but it was always difficult to do anything about it. But now we have the opportunity to do so. So that's a big step forward. Right, a couple more questions, I think, just the last two, short one here. What about GeoGrid? I think it's meant to be on fine-grained soils. May it be physically realistic to replicate field performance? I think it's another reference to fine-grained soils, I'm guessing there.
Well, I haven't looked at this, so a similar approach may work. I expect if there is a mechanical stabilization benefit, it will be less in fine-grained soils. For the time being, we can't take it into account until we investigate this further. So either we'll do it, or hopefully somebody else as well will be looking into this. We'd like to look at this at some point, but at the moment we just can't really say whether there is an additional stabilization benefit.
Okay, thank you, Andrew. I think the last question actually is something I was probably going to ask you as well, but it's a good evening, very interesting presentation. This is from Ting Chong Fong. What do you think if the stability of the reinforced soil was checked using normal limiting equilibrium method, limit state design, I think, compared to what you've been talking about? And I think it might be worth just mentioning briefly the ULS. I think we're talking about the ULS situation here.
Yeah, that could be looked at potentially. I mean, in the early stages of this, we were looking at enhanced cohesion. So maybe you could put an additional cohesive strength into a limit equilibrium model to get the higher strength that way. You could use a higher friction angle. The problem, of course, with all these approaches is that the failure envelope is non-linear. So you need to be very careful with the stress level in your particular problem, which you won't know accurately in a limit equilibrium model. So this approach is definitely better in FEA, where with the new model, it's non-linear, so the failure envelope is always closely matched with the correct stress state. Or with this bilinear approach that I showed for the reinforced soil wall, we've been very careful to monitor the stress level to ensure that our strength parameters are appropriate. There's no reason why those same strength parameters could not be applied to limit equilibrium, but you just need to be very careful about the stress level, and it's more difficult to monitor the stress level in a limit equilibrium approach.
I'd have to say on my part, Andrew, I did try it for the Japanese trial wall just to see how it worked out. Yes, you can get something reasonable, but I don't think it's the right way to do it. But it's not impossible. But I think better in those situations to use the approaches you've been talking about today. You know, I think that brings us to the bottom end of the list of questions that I've found. So I think I'll probably get a little message from the organizers in a minute telling me that it's probably a good time to bring your presentation to an end. So I shall do that. Andrew, I'd first of all like to thank you very much for presenting a lot of incredibly interesting data where we see the combination of both carrying out some fairly fundamental testing, combining it with analysis, and ending up with models. I think this is a very powerful message. And I think also what it's doing is taking out the guesswork, which sometimes has to get used to actually get the results that we see from monitored structures. And I thank you very, very much for that presentation. Also, all the work you put into it. And although you put my name on that paper, all those difficult things were done by you, Andrew. I'd like to mention that again. And but I think, I mean, that particular piece of work was wonderful. A wall where they removed the reinforcement effect gradually. Just a brilliant piece of work. If any university people are listening in and would like to try and do something similar again, I think would be very interesting to hear about it. So yeah, wonderful. Okay, well, Andrew, yes, thank you again, and thank you for, well, luckily your time of the day is not too difficult in Cyprus at the moment, so probably you're off to have lunch or something soon. I'm not quite sure where you've got to, but thanks on behalf of the Indonesian chapter of the IGS. Thanks for all your time, experience, and knowledge you put into this. And we're going to be planning more events next year. You've heard, and just to let everybody know, we'll probably start in February. We may have some slight changes in the way we assemble these events. We may have some more discussion type events, but there will be further webinars as well. So we're still making plans. And Andrew, we might see you back again if we have someone wants an in-depth discussion, say on FEA techniques with a number of people taking part. It's I think it's an area which needs to be talked about. And yeah, thanks again. Okay, so I think I'll be handing back now to the organizers. So Rifa, are you ready there? And please, Andrew, yep, stay on for the quiz just to see if anyone gets your questions right. And
I will.
Have a very good end to the year, and Happy New Year and everything else.
Yep, thank you. My pleasure. And thank you to everyone that's attended today. Thank you very much for attending. Hope you found it interesting. And season's greetings and a Happy New Year to everyone.
Okay, once again, thank you, Andrew Lees, for your excellent presentation. And thank you also to Bapak Mike Doby for guiding the session. Next, I would like to invite all of you for the chance to get the very interesting prize for the total of 250,000 rupiah for 2 winners by joining a very short game we have prepared. The questions would be from Andrew Lees, and the first winner will get 150,000 rupiah, and the second winner will get 100,000 rupiah. To give you a disclaimer before we play, everyone can join this quiz, but for technical reasons, only those who live inside Indonesia are eligible to get the prize. So you can now directly go to your browser on your phone or your PC and type menti.com, menti.com, menti.com. And you have to type the code number shown on your screen or also there in the chat box. The code is 14607737. Once again, the code is 14607737. And once you go there, you have to submit your name and make sure it is the name that you submit in the registration for this webinar. If you forget, you can look at your Zoom and it will be the display name that you use for the Zoom. So later, if you win, the committee will easily contact you for the prize. So remember, the prize is very interesting, 250,000 rupiah total for 2 winners. The first winner will get 150,000 rupiah and the second winner will get 100,000 rupiah. And you will not want to miss this chance. So for those who live inside Indonesia or everyone who wants to play this game, please go to menti.com and put the code 14607737 and fill in your name. We will be waiting for more attendees to join. Meanwhile, I'm going to share my screen and let's see how many has joined. Okay, we're still waiting. Go to menti.com and use the code 14607737. You can see it on your screen or also on the chat box. Wait a minute. Okay, I'm going to share my screen. We're still waiting. I'm going to count down a little bit later. We see here we have 34 participants. We're still waiting for more. You have the chance to win 250,000 rupiah. The first winner will get 150,000 rupiah and the second winner will get 100,000 rupiah. So go to menti.com right now. It can be from your PC or your smartphone and type the code 14607737 and don't forget, please fill in your full name or your the name that you submit in the Zoom registration. Okay, I'm going to count down now. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We're going to play now. Let's see the first question. Answer fast to get more points. To simulate the time-dependent creep of geogrid, which constitutive model type is the most appropriate? A, viscoelastic, B, linear elastic, or C, elastoplastic? Is it the first option? Is it the second option? Or is it the third option? You have 30 seconds from now. To simulate the time-dependent creep of geogrid, which constitutive model type is the most appropriate? Is it A, viscoelastic? Is it B, linear elastic? Or C, elastoplastic? 10 more seconds. You have to answer fast and also correct to gain more bonus point. 3, 2, 1. Time's up. Let's see what is the correct answer. The correct answer is A, viscoelastic. Let's see who leads the first question. For the first question, the fastest one and the correct one is Melissa. Let's see second question. You still have time and have the chances to go on first and second. Answer fast to get more points. What is the distinguishing feature of the Tensar stabilized soil constitutive model? Is it A, strain-dependent stiffness, B, void ratio-dependent permeability, or C, nonlinear strength envelope? Is it A, is it B, or is it C? What is the distinguishing feature of the Tensar stabilized soil constitutive model? Remember, A, B, or C? These questions are all prepared by Andrew Lee, so you should have guessed the answers. You have 10 more seconds. Is it A, B, or C? 5, 4, 3, 2, 1. Time's up. Let's see the correct answer. Oops. The correct answer for the second question is C, nonlinear strength envelope. Okay, for the second question, who leads the leaderboard? The fastest is Hugh Nguyen. Let's see who will win. Top two will get the prize of 250,000 rupiah. Last question, everyone. Question 3 of 3, answer fast to get more points. What was the unusual feature of the PWRI Japan trial walls presented? Is it A, the geogrid was cut internally to shorten its effective length? B, a lightweight fill was used in their construction? Or is it C, earthquake shaking was simulated? You have 30 seconds to answer, but if you answer correct and faster, you'll get bonus point. Only 2 winners. The first winner will get 150,000 rupiah and the second winner will get 100,000 rupiah. So the total is 250,000 rupiah. Are you the two who will win this quiz? Okay, 5, 4, 3, 2, 1. For the last question, the answer is it's A, the geogrid was cut internally to shorten its effective length. Let's see who are the top 2 who will win the money of 250,000 rupiah. Okay, congratulations to Hugh Nguyen Huang Trong with 2,929 points. And the second winner is Christakis Lereidis with 2,852 points. Congratulations to the two winners. The committee will soon contact you to give you the prize. Okay. We would like to remind you that you can register as INA-IGS individual members by clicking the link bit.ly/member INA-IGS also, okay? Ladies and gentlemen, we have now reached the end of the event. Before you leave this webinar, we would like to inform you that you can access your e-certificates and the soft copy material from the speaker by visiting the link bit.ly/info-INA-IGS12. And after filling the quick survey, you will be redirected to the e-certificates. Once again, thank you for your participations. Also, thank you for Andrew Lees and also Bapak Michael Dobi. We hope we can see you at the next event in next year. And finally, good evening and stay healthy, everyone. And see you next year.